For all the years of our lives, we have used the specialized nerve cells called neurons in our brains to make the decisions which control our bodies. But using our neurons to tell apart a house cat sitting in a loaf from an actual loaf of bread is very strenuous. So, with the power of modern computational technology, why not make those inferred choices automatically?
But as much as we would like to directly tell a computer how to recognize the whiskers and tail of a Maine Coon without it mistakenly identifying our pet as something to spread jam on, or vice versa, that is very hard to do, unless the machine already possesses some general intelligence beyond the bare metal. It does exactly only what it's been told. So how do we proceed?
One very old solution for this dilemma, one that almost as old as visual computer itself, is stimulate a real brain on a computer. Again, this is very hard, but attempts that have been made have met with success. The atom of the neural network, as they are called, a neuron.
According to an article titled From the Neuron Doctrine to Neural Networks, published in 2015, in general, a neuron is a single processing element, a logical unit of computation that will take many inputs and by performing a mathematical operation on them, send exactly one output to wherever it needs to go. In short, one neuron, despite the number of inputs it receives, makes one decision per computation.
Now, neurons may work differently in human beings than in electronic implementations, but the analogy of decision-making units working together to perform complex tasks still holds.
Neurons made of silicon-based transistors are distinguished from those made from carbon-based nerve cells merely by calling them artificial.
According to Artificial Neural Networks, published by the IEEE Press in 1992, one neuron connected to some other input neurons would correspond to one of what's called an instar in machine learning terms. If we represent the data numerically in our image recognition model, each neuron has inputs, numbers which can be provided externally or by other neurons.
Weights to assign relative importance to each input, a bias to shift or bias the weighted inputs by a certain amount, and an activation function to map the inputs, weights, and bias to their final output.
An instar functions as the pattern encoder of a network. Meanwhile, the outstar functions as the pattern decoder or recognizer of a network. It has one input but many outputs. Its purpose is to construct the desired output pattern, like bread for a given encoding, like loaf.
So, in a typical neural network that programmers would train and use to recognize some pattern in real applications, there are multiple layers of neurons connected to each other in a series.
To train it, we start with the output that we want for a given input, then use this kind of math called particle differential equation to decide how much each weight and bias parameter needs tweaking.
To use it, they give the network an input and have it compute an output, propagating the data forward.
Lastly, one might notice that more neurons are added to the network. The more of these parameters appear, way too many for the computer's memory to store. One solution that makes sense for images and other spatial data is to store only those parameters which connect inputs or neurons that are nearby.
This can divide the number of parameters in a neural network by 1,000 or more with only minimal loss of error. This type of network would be called a trimmed neural network.
There's a lot more we could have covered about neural networks, but that's going to end it for this video.
Thanks for
watching.